Something is spinning in our solar system that shouldn't exist. 3I-ATLAS arrived from interstellar space in July 2025, and at first glance, it looked like every other comet. Ice, dust, a glowing tail. But when independent observers pushed image processing to its limits, they uncovered a core that appears solid, metallic, rigid. Around it, a clockwise vortex of what some claim is ionized nickel gas, a structure that, according to standard physics, cannot form naturally. Space agencies insist there's nothing to see here, but the processed images tell a different story. By the end of this investigation, you'll understand why some researchers believe we're looking at a dynamo, a cosmic power generator, and why that possibility is both thrilling and deeply unsettling. Keep watching. The evidence is stranger than you think. If you're as captivated by this mystery as I am, go ahead and like this video and subscribe so you catch every development as this story continues to evolve. Leave a comment telling us where you're watching from, what hour of the night or day it is for you right now, and whether you think we're being told everything about what's really happening out there. Part 1. The image that broke the conversation. Picture this. A photograph lands on your screen at 3 in the morning. You've seen hundreds of comet images before, maybe thousands. Fuzzy glowing blobs with tails stretching across the darkness, each one a cosmic snowball doing exactly what comets are supposed to do. Then you see this one, and something in your brain just stops. This is 3I-ATLAS, an object that entered our solar system in July of 2025 from somewhere beyond the stars. The official images released by NASA and the European Space Agency show exactly what you'd expect. There's a bright central region called the coma, where ice and dust spray outward from the nucleus. There's a tail pushed back by solar radiation and the solar wind. It looks like a comet. It behaves like a comet. The agencies tell us it is a comet. Full stop. Nothing to see here. But then, late November 2025, someone decided to look harder. Amateur astrophotographers, working independently across different continents, took the raw telescope data and pushed it through specialized processing pipelines. They stacked multiple exposures, filtered out noise, cranked up the contrast, adjusted the dynamic range until faint details emerged from the darkness. What they claim to have found underneath that blinding coma is something that shouldn't exist. The processed frames show a rigid, elongated core. Not a fuzzy blob of outgassing ice, but something with sharp edges, with structure, with what looks like tensile strength. Around this core, spiraling in a tight clockwise pattern, is a glowing envelope of material that some observers have described as looking like a hurricane seen from space. Not a diffuse cloud expanding symmetrically outward, but organized, rotating, coherent. The images first appeared online under handles like Red Collie, Ray's Astrophotography, Diego San Araujo. Within 48 hours, the conversation around 3I-ATLAS completely changed. Forums exploded with speculation. Was this image processing artifact an illusion created by over-aggressive enhancement? Or had these amateur observers actually peeled back the veil and seen something no one was supposed to see? Here's what would have to be true for this structure to be real. You'd need a core made of something strong enough to hold its shape under the stress of interstellar travel, solar heating, and gravitational forces. You'd need ionized gas, probably heavy elements like metals, behaving in a coordinated way rather than just expanding randomly into space. You'd need magnetic fields, electric fields, or both, powerful enough to shape the flow of charged particles into that spiral pattern. And you'd need all of this to happen naturally, in an object that supposedly formed billions of years ago in some distant protoplanetary disk, and just happened to wander into our neighbourhood. Or, and this is where things get uncomfortable, you'd need something that wasn't formed naturally at all. The hypothesis being floated in certain corners of the internet is that 3I-ATLAS isn't a comet, it's a dynamo, a massive electromagnetic machine operating in deep space, generating its own magnetic field, spinning ionized gas around a metallic core like some kind of cosmic motor. If true, this would be the most significant discovery in human history. It would mean we are not alone. It would mean someone, or something, built this object and sent it through the galaxy, and it's here right now, less than 2 astronomical units from Earth. But we have to be honest about what we're dealing with. Every astronomical image is the product of choices. Exposure time, wavelength filters, stacking algorithms, noise reduction methods, contrast curves. Push any of these parameters hard enough, and you can create the illusion of structure where none exists. You can turn random fluctuations in pixel values into edges, patterns, spirals. This is especially true for faint objects where the signal-to-noise ratio is already terrible. And 3I-ATLAS, despite being relatively bright for an interstellar visitor, is still faint enough that pulling details out of the outer coma requires extreme processing. The major observatories haven't confirmed any of this. Hubble Space Telescope images show a normal-looking comet. The Lucy spacecraft, which happened to be in the right position to observe 3I-ATLAS during its closest approach, captured images that NASA describes as entirely consistent with cometary behaviour. The James Webb Space Telescope conducted spectroscopy and found a coma dominated by carbon dioxide, water, carbon monoxide and dust. Nothing in the official record suggests anything unusual about the nuclear structure. So we're left with two very different data sets. On one hand, calibrated observations from professional instruments following rigorous scientific protocols. On the other hand, heavily processed frames from amateur equipment showing structures that, if real, would rewrite astrophysics. The tension between these two views is what makes 3I-ATLAS so fascinating and so frustrating. What if the spiral is real? What if there really is a rigid core underneath all that gas? What would it take to prove it? And more importantly, what would it take to explain it without invoking aliens or advanced technology? Because that's the knife edge we're walking here. Either this is the most extraordinary natural object ever observed, or it's something else entirely. There is no comfortable middle ground. In the next section, we're going to dig into those processed images themselves and ask the hard questions. What steps were taken to create them? What kinds of artifacts can those steps introduce? How do you tell the difference between real structure and digital illusion? Because before we can talk about dynamos and magnetic cores and spiraling plasma, we need to know if we're even looking at something real. Part 2. What the processed images actually show and where doubts begin. Every photograph is a lie. That's not cynicism, it's just physics. The moment light hits a sensor, reality becomes data, and data becomes subject to interpretation. In astronomy, this process is amplified 1,000-fold because the objects we're trying to see are so faint, so distant, so overwhelmed by noise that extracting a signal requires layers upon layers of computational manipulation. Let's walk through what it takes to create one of these controversial images of 3I-ATLAS. First, you collect multiple raw exposures of the same field, each one a grid of pixel values representing photon counts. These frames are dark, noisy, filled with cosmic ray hits and electronic artifacts. You stack them together, aligning carefully to average out the random noise and boost the true signal. Already you've made choices about alignment algorithms, rejection thresholds, weighting schemes. Next comes calibration. You subtract dark frames to remove thermal noise from the sensor. You divide by flat fields to correct for uneven sensitivity across the detector. You apply bias correction, sky background subtraction, maybe even attempt to model and remove the point spread function caused by atmospheric turbulence or telescope optics. Each step introduces assumptions about what the instrument is doing and what the object should look like. Now the real manipulation begins. You stretch the brightness scale to reveal faint details. This isn't just turning up contrast on a regular photo. It's applying nonlinear transformations that can amplify subtle variations by orders of magnitude. Logarithmic scaling, histogram equalization, adaptive filters that boost certain spatial frequencies while suppressing others. You apply noise reduction algorithms that try to distinguish random fluctuation from real structure, but these algorithms don't know the difference. They just apply statistical rules. Sometimes they guess wrong. Then comes sharpening. Unsharp masking, deconvolution techniques that attempt to reverse the blurring caused by the instrument's optics. These methods are powerful but dangerous. They can turn a barely resolved smudge into a crisp edge. They can make diffraction artifacts look like physical jets. They can create the illusion of fine detail that was never captured by the telescope in the first place. Here's the problem. In a faint low signal to noise environment like the outer coma of 3I-ATLAS, all of these processing steps are walking a tightrope. The fainter the feature, the more it resembles noise, and the more aggressive processing is needed to see it. But aggressive processing is exactly what creates spurious structures, halos around bright regions, linear streaks from imperfect cosmic ray removal, tendrils that are really just noise amplified into visibility, ghost edges from sharpening filters, the point, spread function, the characteristic blur pattern of the telescope, can leave residuals that look like spiral structure if you're not careful. Every bright star in the field creates a diffraction pattern with spikes and rings. If 3I-ATLAS passed near such a star during the exposure, those diffraction artifacts could be misinterpreted as features of the comet itself. This isn't speculation. It's a known failure mode in astronomical image processing. So when we see these processed frames showing a rigid elongated core and a clockwise spiral, we have to ask, has anyone independently reproduced this result using a completely different processing pipeline? Have multiple observers, using different telescopes at different locations, all seen the same structure? As far as publicly available information goes, the answer is no. The major professional observatories have not confirmed this morphology. The spacecraft images from Lucy and Hubble show standard cometary appearance. NASA released a statement just weeks ago saying 3I-ATLAS looks and behaves like a comet, with no technosignatures detected. That's about as close to a definitive rejection as you'll get from a space agency without calling someone out directly. The European Space Agency's observations concur. Ground-based professional campaigns using the Very Large Telescope, the Nordic Optical Telescope, and others have published results describing 3I-ATLAS in conventional terms. Coma, tail, dust, gas, outgassing behaviour consistent with a volatile rich nucleus. We're dealing with two fundamentally different kinds of data here. Professional instruments operate with calibrated sensors, well-understood optics, rigorous quality control, and conservative processing designed to preserve fidelity. Amateur setups, while increasingly sophisticated, often lack this infrastructure. Raw frames might not have proper calibration data. Processing might be done with consumer software designed for aesthetic results rather than scientific accuracy. And there's a selection bias. Amateur observers tend to share their most interesting results, not the hundreds of frames where nothing unusual appeared. This doesn't mean the amateurs are wrong. History is full of cases where amateur astronomers made legitimate discoveries that professionals initially dismissed. But it does mean we need extraordinary caution. The burden of proof is high. If the core and spiral are real, if they represent actual physical structure rather than processing artifacts, then independent teams should be able to reproduce them reliably. That hasn't happened yet. But let's entertain the possibility for a moment. What if some real structure does exist in the data, buried under noise and outgassing, and the heavy processing is actually revealing something legitimate? If that's true, we need to ask what kind of physics could produce it. Because a rigid core and organised spiral are not what you expect from a comet. Comets are messy. They fragment. They outgas asymmetrically. Their nuclei are rubble piles held together weakly by gravity and ice. Nothing about them suggests the kind of structural integrity these images seem to show. Which brings us to the bold, speculative and frankly unsettling hypothesis that's been circulating since these images emerged. What if 3I-ATLAS has a magnetic core? What if it's generating electric and magnetic fields strong enough to shape the behaviour of ionized gas around it, forcing charged particles into spiral trajectories, creating an organised plasma envelope that looks nothing like a normal cometary coma? What if it's not passive but active, not a snowball but a machine? In the next section, we're going to explore exactly how that could work, the physics of charged particles in electromagnetic fields, the concept of a unipolar dynamo operating in space, the Lorentz force, magnetohydrodynamics, and what it would take to make a cosmic hurricane out of ionized metal gas. It's speculative, it's unproven, but it's also not impossible, and that's what makes it so compelling. Part 3. The Lorentz force dynamo hypothesis. How, in theory, this could happen. Imagine you have a magnet, a big one, powerful, maybe the size of a building. Now imagine it's spinning in space, surrounded by a cloud of ionized gas. The gas isn't neutral, it's plasma, meaning the atoms have been stripped of electrons, leaving behind positively charged ions and free electrons, all of them moving, drifting, responding to forces. Now here's where it gets interesting. When a charged particle moves through a magnetic field, it doesn't just keep going in a straight line. It feels a force perpendicular to both its velocity and the magnetic field direction. This is the Lorentz force, one of the fundamental laws of electromagnetism. The formula is simple. Force equals charge times the sum of electric field plus velocity cross product with magnetic field. In symbols, F equals Q times quantity E plus V cross B. But the consequences are anything but simple. If you have a magnetic field pointing in one direction and charged particles moving in another, the Lorentz force will make them curve. And if the geometry is right, they'll curve into spirals, orbiting around magnetic field lines like beads on a wire. This happens in Earth's magnetosphere. It happens in solar flares. It happens around pulsars. Wherever you have plasma and magnetic fields together, you get organized, flowing structures that look nothing like random gas clouds. Now apply this to 3I-ATLAS. Just suppose that underneath all the outgassing and dust, there's a core made of metal. Iron, nickel, maybe other heavy elements. Not just solid rock with traces of metal, but metal rich enough to be electrically conductive, magnetically active. And suppose this core is magnetized, either from its formation or from some internal dynamo process. It's generating a magnetic field, maybe not as strong as Earth's, but strong enough to influence the behavior of plasma nearby. As the object moves through space, it heats up approaching the sun. Material on the surface begins to sublimate or vaporize. But instead of normal comet ices, water and carbon dioxide and frozen gases, suppose at least some of what's coming off is metal vapor, nickel gas, iron vapor, other heavy elements. These are much easier to ionize than water. Ultraviolet light from the sun will strip electrons off metal atoms far more readily than off stable molecules like carbon dioxide. So you end up with a cloud of ionized metal surrounding the core. Here's where the Lorentz force comes in. If the core is magnetic and the gas is ionized, the Lorentz force will organize the plasma into spiral trajectories. Particles will follow magnetic field lines, curving, rotating, creating a coherent structure instead of just expanding outward symmetrically. If there's also an electric field, maybe from charge separation between the core and the surrounding plasma, that adds another component to the force. The particles spiral faster, tighter, forming what could genuinely look like a hurricane pattern when viewed from the side. This isn't wild fantasy. It's mainstream physics, just applied to an unusual scenario. The concept of a unipolar dynamo, where a rotating conductor in a magnetic field generates an electric current and perpetuates its own magnetic field, is well understood. We've built them in laboratories. Jupiter's moon Io creates one naturally, interacting with Jupiter's magnetic field and generating millions of amps of electric current that flow between the moon and the planet. Pulsars are essentially giant rotating magnets, with plasma spiraling around them at relativistic speeds. The question is whether 3I-ATLAS could be doing something similar on a smaller scale. For this to work, you'd need several things. First, a core with enough metallic content to be magnetically significant. Second, a mechanism to generate or sustain the magnetic field, either remnant magnetization from formation or some kind of internal dynamo. Third, a source of ionized material, which could be metal vapor sublimating from the surface. Fourth, enough structural integrity for the core to maintain its shape and rotation under the stress of solar heating and solar wind pressure. Let's run some rough numbers just to see if this is physically plausible. Suppose the core is about 1 kilometer across and made primarily of iron-nickel alloy, like the core of a differentiated asteroid. Its mass might be on the order of 1 billion tons. Suppose it's magnetized to a field strength of 1 Tesla at the surface, comparable to a strong laboratory magnet but millions of times weaker than a neutron star. That's not unreasonable for a metallic body with some internal motion or residual magnetization. Now suppose it's outgassing metal vapor at a rate of, say, 10 kilograms per second. That's tiny compared to normal comets, which can expel thousands of kilograms per second of water and dust. But metal vapor is denser and more easily ionized, so even a small rate could create a significant plasma cloud. If the Lorentz force organizes this plasma into spiral trajectories with velocities of a few kilometers per second, you'd get visible structures on scales of tens to hundreds of kilometers. Could this produce the observed spiral pattern? In principle, yes. The numbers aren't crazy. The physics is real. But here's the problem. Where does the energy come from? Maintaining a magnetic field and driving plasma flows requires power. A remnant magnetic field will decay over time due to resistive losses. A dynamo needs rotation and internal motion, which means kinetic energy that eventually dissipates. If 3I-ATLAS is billions of years old, as an interstellar wanderer would be, any internal energy source should have exhausted itself long ago. Unless And this is where things get really speculative. The object isn't as old as it seems, or it's been recharged somehow during its journey, or there's an energy source we don't understand, or the possibility no one wants to say out loud it was built to do this. The unipolar dynamo hypothesis treats 3I-ATLAS like a natural phenomenon, but the level of organisation and sustained activity it would require starts to blur the line between natural and artificial. If you can build a magnetic dynamo that operates for millions of years in deep space, generating plasma flows and spiralling envelopes, you've essentially built a machine. Whether that machine was made by geological processes or by engineers becomes a question of theology as much as physics. But before we go down that road, we need to address the other bold claims circulating alongside the processed images. The claim that spectroscopy shows ionized nickel gas in the coma of 3I-ATLAS. If true, that would be a smoking gun for the metal core hypothesis. Heavy metals don't just appear in cometary comas. They require special circumstances, high temperatures, strong radiation, unusual composition. If 3I-ATLAS is venting nickel vapour, that changes everything. So in the next section, we're going to examine that claim closely. What does the spectroscopic data actually show? And what would it take to prove that heavy metals are really there? Part 4. Spectral claim, ionized nickel, and what that would imply. Let's talk about how we know what anything in space is made of. You can't reach out and touch a comet. You can't bring 3I-ATLAS into a laboratory and run a chemical analysis. All you have is light, photons that travelled from the object to your detector, carrying information encoded in their wavelengths. And the way you decode that information is spectroscopy. Every element, every molecule, every atom has a unique fingerprint. When electrons jump between energy levels, they emit or absorb light at very specific wavelengths. Hydrogen does it at 656 nanometers in the red and 486 nanometers in the blue. Sodium produces a bright doublet in the yellow. Iron has thousands of lines scattered across the spectrum. If you spread out the light from an object into a rainbow and look carefully, you can see these lines and identify what elements are present. It's one of the most powerful tools in astronomy. When people claim that 3I-ATLAS is showing ionized nickel in its coma, this is what they're implicitly referring to. They're saying that spectroscopic observations have detected emission lines characteristic of nickel ions, meaning nickel atoms that have lost one or more electrons and are glowing in space. If true, this would be extraordinary. Nickel is a heavy metal. It doesn't sublimate easily. Solid nickel doesn't turn into gas until you heat it to over 3000 degrees Kelvin. That's hotter than most cometary surfaces ever get, even at perihelion. But here's where we need to be very careful. Saying that something looks a certain colour is not the same as doing spectroscopy. A photograph might show a comet with a greenish tint, but that doesn't tell you what's causing the colour. It could be cyanogen, or diatomic carbon, or molecular emissions from various radicals, or even just dust scattering light in a particular way. Colour is ambiguous. Spectral lines are not. So what does the actual spectroscopic data for 3I-ATLAS show? The most detailed observations we have come from the James Webb Space Telescope, which observed the comet with its near-infrared spectrograph during its approach to the Sun. The results were published in preprint form in late 2025. The dominant feature in the spectrum is carbon dioxide. Strong emission bands throughout the infrared. Water is also present, both as gas and as ice particles. There's carbon monoxide, carbonyl sulfide, and various dust features. This is exactly what you'd expect from a volatile-rich comet formed in a cold protoplanetary disk. There is no mention of nickel. There's no mention of iron or any other heavy metal emission. The spectrum is consistent with ices, organics, and silicate dust. Everything normal, nothing exotic. Other observations reinforce this. Ultraviolet spectroscopy detected hydroxyl, the dissociation product of water, confirming active water sublimation. Optical spectroscopy from ground-based telescopes identified typical cometary emission lines. Neutral carbon, ionized carbon monoxide, sodium from dust grains. Again, nothing unusual. Certainly nothing suggesting metal vapour. So where does the nickel claim come from? It appears to originate from visual impressions of colour in heavily processed images. Some of the enhanced frames show a bluish or metallic tint to the inner coma, and this has been interpreted by some observers as evidence of metal gas. But this is exactly the kind of inference you cannot make without proper spectroscopy. Colours in images can be deceiving, especially after heavy contrast adjustment and noise reduction. Molecular emissions, dust properties, scattered light, even processing artifacts can all produce colour shifts that have nothing to do with composition. There's another issue. Even if nickel were present, detecting it would be difficult. Nickel's strongest emission lines are in the ultraviolet and the visible, but they're relatively weak compared to the overwhelming light from normal cometary emissions. You'd need high spectral resolution, good signal-to-noise, and careful calibration to isolate those lines from everything else. To date, no such detection has been reported in peer-reviewed literature. If it existed, it would be headline news. The discovery of significant metal vapour in an interstellar comet would be an extraordinary result, demanding immediate follow-up and verification. Now, let's entertain the idea for a moment. Suppose future observations do detect nickel emission, or iron, or other heavy metals. What would that mean? First, it would strongly suggest that 3I-ATLAS has a composition very different from typical comets. Instead of being mostly ice and rock, it would have to have significant metallic content, either in the nucleus or in large dust grains that can vaporize. Second, it would imply high temperatures or intense radiation, enough to turn solid metal into gas. That's not impossible near the Sun, but it would be unusual for a comet that brightens so far from perihelion. Third, it would lend credibility to the idea that this object might be a fragment of a differentiated body, maybe a planetary core that was stripped and ejected from its original system. But we're not there yet. The spectroscopic evidence we have does not support the nickel hypothesis. The data shows a normal, albeit unusual, volatile, rich comet. CO2 dominated with water and organics, exactly as you'd expect from an icy body formed far from its parent star. The nickel claim, as it stands, is speculative, based on indirect inference and visual impressions rather than hard spectroscopy. This is a crucial point because the entire dynamo hypothesis hinges on having ionized metal gas. Without that, the Lorentz force scenario falls apart. You can't create organized plasma spirals if the plasma is just ionized water vapor and carbon dioxide. Those molecules are too light, too easily dissociated, too diffuse. The dynamo idea needs heavy ions, high conductivity, strong coupling to magnetic fields. Nickel and iron would provide that. Water and CO2 do not. So we're left in an uncomfortable position. The processed images suggest structures that might require metal plasma to explain. But the spectroscopy says no metal is present. Either the structures aren't real, or they're being produced by some other mechanism we haven't thought of, or there's something missing from the spectroscopic data. None of these options are satisfying. In the next section, we're going to step back and look at how the scientific community has reacted to all of this. What are the official statements? What data has been released, and what's being held back? And why do some people believe that agencies are intentionally hiding evidence? Because this isn't just a scientific dispute anymore. It's become a question of trust, transparency, and who gets to decide what counts as truth. Part 5. Mainstream reactions, skepticism, data requests, and the censorship narrative. When strange claims emerge from the fringes of the internet, the usual response from institutional science is silence. Not because scientists are hiding something, but because responding to every speculative idea would consume all their time. But 3I-ATLAS has become impossible to ignore. The images, the theories, the sheer volume of public interest has forced space agencies to address the controversy directly, and their response has been swift and unequivocal. NASA released a statement in late November 2025 clarifying that 3I-ATLAS looks and behaves like a comet, with no evidence of anomalous structure or technosignatures. A spokesperson emphasized that multiple observations from spacecraft, including Lucy, Hubble, and ground-based telescopes, all show standard cometary morphology. The European Space Agency echoed this position, noting that polarimetric studies, spectroscopy, and photometry are all consistent with a volatile rich nucleus undergoing normal sublimation-driven outgassing. The data they're citing is substantial. Hubble captured high-resolution images showing a diffuse coma and tail with no indication of a rigid core or organized spiral. The Lucy spacecraft, despite being at a favorable geometry, reported cometary appearance with no unusual features. The James Webb Space Telescope's near-infrared spectroscopy provided detailed compositional analysis showing carbon dioxide, water, and dust. Ground-based campaigns using professional instruments like the Very Large Telescope measured polarization, finding that 3I-ATLAS exhibits behavior different from solar system comets, but still within the range of natural objects, likely due to unusual dust grain properties. All of this points to one conclusion. 3I-ATLAS is weird, yes. It's an interstellar visitor with unusual composition and polarization behavior, but it's still a comet. Icy nucleus, outgassing coma, dust tail, all the standard features. Nothing in the professional data suggests a metal core, ionized plasma spirals, or electromagnetic activity. So why do the amateur processed images look so different? The agencies argue it's a matter of processing. Heavy contrast enhancement, aggressive noise reduction, and sharpening applied to faint low signal to noise data can create spurious structures. What looks like a rigid core might just be over-sharpened coma. What looks like a spiral might be edge enhancement artifacts or diffraction residuals. Without access to the exact processing pipeline used, it's impossible to say for certain. But the fact that no independent team using calibrated instruments has reproduced the same morphology is telling. This is where the censorship narrative begins. Online communities have claimed that official releases have been scrubbed or sanitized to hide anomalous structures. The argument goes like this. The raw frames captured by spacecraft and professional telescopes originally showed the same features visible in amateur processed images, but before public release, those features were removed or blurred out through deliberate manipulation. Only amateurs who captured their own raw data, or who accessed frames before processing, can see the truth. The motivation for such censorship, according to proponents, ranges from avoiding public panic to suppressing evidence of extraterrestrial technology. Some claim that governments have protocols for handling potential alien artifacts, and that 3I-ATLAS triggered those protocols. Others suggest more mundane reasons, like agencies not wanting to admit they missed something, or not wanting to deal with the media frenzy that would follow a genuine anomaly. Let's evaluate this seriously. Could a space agency like NASA deliberately alter or withhold data? Technically, it's possible. Data pipelines involve many processing steps, and choices about compression, calibration, and noise filtering could, in principle, be used to obscure features. But practically, the logistics are daunting. Multiple telescopes, multiple teams, multiple countries, all observing the same object. Coordinating a cover-up across all of them would require unprecedented cooperation and secrecy. Scientists are competitive, institutions are bureaucratic, and leaks are common. Keeping a secret of this magnitude would be nearly impossible. There are more mundane explanations for differences between official and amateur images. Professional instruments prioritize calibration and fidelity over aesthetics. They apply conservative processing to avoid introducing artifacts, which means faint details might be suppressed. Amateurs, working without the burden of peer review, can push processing much harder, revealing features that may or may not be real. Timing matters too. Different observations at different dates and different viewing geometries will show different aspects of the coma. Spacecraft images might be taken when the coma is bright and diffuse, while amateur images might catch a moment when it's more structured. But let's say, for argument's sake, that there's no conspiracy, just delays and institutional caution. The scientific community still has a responsibility to address these claims properly. If amateur observers are seeing structures that professionals aren't, the solution isn't dismissal, it's investigation. Release the raw data. Let independent teams reprocess it. Compare pipelines, test for artifacts, run simulations, do the science. Some researchers have called for exactly this. Open letters and petitions have circulated, asking NASA and ESA to release unprocessed spacecraft frames with full metadata. The goal is transparency, not confrontation. If the core and spiral are artifacts, independent analysis will show that. If they're real, independent analysis will confirm it. Either way, the community benefits. What would it take to settle this conclusively? 3 things. First, full release of raw frames from all spacecraft and professional telescope observations, along with metadata including exposure times, instrument settings, calibration data, and timestamps. Second, independent reprocessing by multiple teams using different software pipelines, with results published openly for comparison. Third, new targeted observations specifically designed to test for the claimed structures, high-resolution imaging at different wavelengths, spectroscopy aimed at detecting metal emissions, polarimetry to probe dust and plasma properties, and if possible, in situ measurements from a probe. None of this has happened yet. The data releases so far have been standard calibrated images, not raw frames. The reprocessing has been limited to amateur efforts with unknown provenance, and new observations, if they're being planned, haven't been announced publicly. The gap between what's needed and what's available is fueling suspicion, but suspicion isn't evidence. The fact that agencies haven't released everything doesn't mean they're hiding something. Data release takes time, calibration is complex, publication schedules are slow, and frankly, agencies might not see the need to respond to every internet theory with the same rigor they'd apply to a peer-reviewed hypothesis. That's frustrating for people who believe they've seen something real, but it's also how institutions operate. The tension here is between two modes of knowledge production. On one side, crowd science, fast, open, driven by curiosity and enabled by accessible tools. On the other side, institutional science, slow, cautious, driven by rigor and constrained by peer review. Neither is perfect. Crowds can generate noise and false positives. Institutions can be slow and dismissive. The ideal is collaboration, but we're not there yet with 3I-ATLAS. So where does that leave us? The mainstream position is clear. Comet, nothing unusual, case closed. The amateur position is equally clear. Something strange is there, and we need better data to understand it. And caught between them is the public, trying to figure out who to trust. In the next section, we're going to dive deeper into dynamics and trajectories, asking whether the way 3I-ATLAS moves through space can tell us anything about what it really is. Because if it's a magnetized dynamo, its trajectory should show it. Part 6. Reconstructing. Trajectories and dynamics for a magnetized object. When an object moves through space, it leaves a trail of clues. Not a physical trail, but a mathematical one. The precise path it takes. The tiny deviations from a perfect gravitational orbit. The subtle accelerations that reveal forces beyond gravity. For comets, those forces are well understood. Outgassing ice creates jets of gas and dust that push against the nucleus, changing its trajectory in measurable ways. Solar radiation pressure exerts force on the coma and tail. The solar wind, a stream of charged particles from the sun, can also interact with ionized gas. All of these effects are small but detectable, with careful astrometric tracking. 3I-ATLAS was discovered on July 7, 2025 by the Asteroid Terrestrial Impact Last Alert System telescope in Chile. The name is bureaucratic but fitting. 3I for third interstellar object, ATLAS for the survey that found it. Within days of discovery, astronomers realized this wasn't orbiting the Sun. It was on a hyperbolic trajectory, coming from interstellar space and destined to leave again. Its path was traced back through the inner solar system and forward to its eventual exit. Perihelion, the closest approach to the Sun, occurred around October 30, 2025, at a distance of roughly 1.4 astronomical units, just outside the orbit of Mars. For a normal comet, perihelion is where activity peaks. Closer to the Sun means more heating, more sublimation, more outgassing. But 3I-ATLAS didn't follow that script. It brightened dramatically when it was still several astronomical units away, far earlier and more rapidly than models predicted. This unexpected behaviour caught attention and led to the intense observational campaign we've been discussing. But what matters here isn't the brightness curve, it's the trajectory. NASA has publicly stated that 3I-ATLAS shows small non-gravitational accelerations, consistent with normal cometary outgassing. These perturbations are in the expected direction, away from the Sun, as gas jets push the nucleus. The magnitude is small, on the order of millimeters per second change in velocity over weeks or months. That's typical for an active comet. It doesn't require exotic explanations. But just suppose that 3I-ATLAS is not just outgassing, but also interacting electromagnetically with the solar environment. If it has a magnetic core and is surrounded by ionized plasma, it could couple to the solar magnetic field. The solar wind carries magnetic field lines with it, and a magnetized object could experience forces from that interaction. Imagine dragging a magnet through a sea of moving plasma. There would be induced currents, electromagnetic drag, maybe even thrust depending on the geometry. These forces would add to or subtract from the radiation pressure and outgassing effects, producing a net acceleration that doesn't align neatly with the Sun object line. What would such a force look like observationally? First, you'd expect deviations in the trajectory that don't correlate simply with distance from the Sun. Normal outgassing produces forces roughly radial, pushing away from the Sun. Electromagnetic interactions could be at angles depending on the orientation of the magnetic field and the solar wind velocity. Second, you might see time variability. The solar wind isn't constant. It has gusts, shocks, magnetic sectors. If 3I-ATLAS is coupling to that environment, its non-gravitational acceleration should fluctuate in response. Third, the plasma tail should show unusual morphology. Instead of a straight ion tail pushed back by the solar wind, you might see kinks, twists, or localized brightenings corresponding to magnetic reconnection events. Have any of these been observed? Not in the publicly released data. The trajectory residuals reported so far are small, steady, and consistent with outgassing. The coma and tail in professional images look like a comet. There's no indication of time variable forces or anomalous accelerations. The astrometric tracking, which is extremely precise thanks to multiple observatories worldwide, shows no unexplained deviations. This is a significant constraint on the electromagnetic hypothesis. If 3I-ATLAS were a powerful dynamo generating strong magnetic fields and driving plasma flows, you'd expect measurable effects on its orbit. The forces involved in maintaining a spiraling plasma envelope would be substantial, and they would couple to the solar wind and interplanetary magnetic field in ways that produce trajectory perturbations. The absence of such perturbations suggests either the electromagnetic activity is much weaker than claimed, or it doesn't exist at all. But there's a loophole. Suppose the forces are real but symmetric. If the magnetic field is aligned with the spin axis, and the plasma flows are organized symmetrically around that axis, the net force might average out. The object pushes plasma outward in all directions, so there's no net thrust. Or suppose the electromagnetic effects are transient, turning on and off, and the current observations haven't caught them in the act. Or suppose the coupling to the solar wind is weak, producing forces below the detection threshold of current astrometry. None of these are satisfying explanations, but they're possible. The problem is that they're also unfalsifiable. If every negative result can be explained away by invoking symmetry or timing or weak coupling, the hypothesis becomes impossible to test. That's a red flag. Good scientific hypotheses make specific testable predictions. If the dynamo hypothesis predicts observable trajectory deviations and we don't see them, the hypothesis is weakened. Hand-waving about why we shouldn't see them doesn't help. As 3I-ATLAS recedes from the Sun, its activity will decline. Outgassing will drop off, the coma will fade, and eventually the object will become too faint to observe from Earth. But before that happens, there's a window for careful tracking. If electromagnetic effects are real, they might become more apparent as the normal cometary forces weaken. In the outer solar system, with less solar heating and less outgassing, any residual magnetic interaction with the solar wind would stand out more clearly in the data. This is a prediction. If 3I-ATLAS is a magnetized object, the next few months of astrometric tracking should show anomalies that normal comet models can't explain. We'll have to wait and see. But for now, the trajectory data doesn't support the dynamo idea. It supports a comet. In the next section, we're going to explore the structural hypotheses in more detail. If this object isn't a normal comet, what could it be? A planetary core fragment? An artificial construct? Some kind of exotic natural body we've never seen before? Each possibility has implications and each has serious problems. Part 7. Structural hypotheses, planetary core fragment versus engineered construct versus exotic natural body. Let's lay out the options. If 3I-ATLAS really does have a rigid metallic core and organized plasma dynamics, and if that's not an artifact or misinterpretation, then we're dealing with something outside the normal taxonomy of solar system objects. There are 3 broad categories it could fall into, each with very different implications for what we think we know about the universe. Option 1. A planetary core fragment. Imagine a rocky planet, maybe Earth-sized or smaller, orbiting a distant star billions of years ago. Something catastrophic happens. A collision with another planet, a close encounter with a stellar companion, or even ejection during the formation of a giant planet. The outer layers are stripped away, leaving behind the dense metallic core. This core, mostly iron and nickel, is flung into interstellar space. It wanders for millions or billions of years, cooling, magnetizing perhaps from residual internal motion until by chance it passes through our solar system and we see it. Could such an object survive the journey? Metal is strong. Iron-nickel alloys have high tensile strength, much higher than ice or rock. They wouldn't fragment or crumble under tidal stresses or radiation pressure the way a rubble pile comet would. A solid metal core could maintain structural integrity across interstellar distances. When it enters the solar system and approaches the Sun, solar heating would affect the surface but not the bulk. Metal has high thermal conductivity, so heat spreads out rather than causing catastrophic thermal stress. You might get some surface vaporization, creating a thin atmosphere of metal gas, but the core itself would remain solid. Now here's the problem: the spectroscopy. 3I-ATLAS shows a carbon dioxide-rich coma, water, ices, organics. Those are volatiles, not metals. If the object were a bare planetary core, where did those volatiles come from? Maybe the core isn't bare. Maybe it accreted a thin veneer of ice and dust during its interstellar journey, passing through molecular clouds or protoplanetary disks. That ice sublimates when heated, producing the observed coma, while the core underneath remains metallic. This is plausible but requires a specific history. The other problem is probability. Planetary cores don't get ejected easily. It takes violent events, and even when they happen, the ejected fragments are more likely to be rocky mantle material than pure metal core. The core is deep inside, protected. Stripping it completely requires extraordinary energy, and even if it happens, the odds of such a fragment wandering into our solar system are astronomically low. We've only identified 3 interstellar objects so far. Having one of them be a planetary core fragment would be an incredible coincidence. Option 2, an artificial construct. This is the explanation no one wants to say out loud, but everyone is thinking. What if 3I-ATLAS isn't a natural object at all? What if it's a machine, a probe, a device built by an advanced civilization and sent through the galaxy for purposes we can only guess at? A magnetic dynamo could be a power source, generating energy from its interaction with stellar magnetic fields or cosmic rays. The organized plasma could be an exhaust, a cooling system, or a form of propulsion. The rigid core could house instruments, computers, mechanisms we don't have names for. If this were true, it would be the most significant discovery in human history. Proof that intelligence exists beyond Earth. Proof that technology can traverse interstellar space. Proof that we're being visited, observed, maybe even studied. The implications for science, philosophy, religion, and geopolitics would be incalculable. But extraordinary claims require extraordinary evidence, and we don't have it. Nothing about 3I-ATLAS's behavior definitively points to artificiality. It doesn't emit radio signals, it doesn't change course, it doesn't exhibit periodic or structured light variations suggestive of rotating machinery. Its trajectory is a passive hyperbola, not controlled flight. And most damning, its coma is full of normal cometary volatiles. If this is a machine, why is it surrounded by water vapor and carbon dioxide? Why does it look, spectroscopically, like a comet? You could argue camouflage. Maybe the probe is covered with ice to avoid detection, to blend in with natural objects. But that requires assuming a level of intention and sophistication that strains credulity. Why would an advanced civilization build a probe, send it across the galaxy, and then go to great lengths to make it look like a comet? If they wanted to hide, they could simply avoid the inner solar system. If they wanted to be noticed, they could signal. The camouflage hypothesis raises more questions than it answers. Option 3, an exotic natural body. Maybe 3I-ATLAS doesn't fit into our existing categories because our categories are incomplete. We've only observed a handful of interstellar objects. Our models of planet formation, comet composition, and interstellar evolution are based almost entirely on solar system data. Maybe out there, in other stellar systems with different formation histories, different compositions, different environments, objects form that we've never imagined. Metal-rich planetesimals, magnetized conglomerates, bodies with unusual volatile mixtures, strange outcomes of collisional evolution or stellar encounters. This is the humble option. Instead of invoking aliens or catastrophic ejections, we simply admit ignorance. 3I-ATLAS might be natural, might be formed through processes we don't fully understand, and might be teaching us that the galaxy is more diverse than we thought. It's Occam's razor with a twist. The simplest explanation is that we don't know everything. and strange things exist naturally without needing special explanations. But even this option struggles with the data. The spectroscopy shows normal volatiles. The trajectory shows normal dynamics. The morphology, when observed with calibrated instruments, looks like a comet. If 3I-ATLAS is exotic, its exoticism is subtle. It's not wildly different, just different enough to be interesting. And that's actually the hardest category to work with, because it requires us to expand our models just a little bit, in ways that are difficult to specify. None of these three hypotheses fits perfectly. The core fragment requires ad hoc assumptions about volatile veneers and unlikely ejection scenarios. The artificial construct conflicts with the spectroscopic and behavioural data. The exotic natural body is vague and difficult to test, yet one of them, or some variant, must be true if the anomalous features are real. And if the features aren't real, if they're artifacts, then we're back to square one. 3I-ATLAS is just a comet, unusually bright and compositionally distinct but fundamentally ordinary. The frustration here is palpable. We have tantalizing hints, ambiguous images, bold claims, and professional data that contradicts most of it. We're stuck in a liminal space between discovery and debunking, unable to move decisively in either direction without more evidence. In the next section, we're going to step back from the object itself and look at the process. How crowd science and institutional science are colliding over 3I-ATLAS, and what that tells us about the future of astronomy in an age of open data and social media virality. Part 8. Crowd science versus institutional science. Pipelines, incentives and failure modes. There's a quiet revolution happening in astronomy, and 3I-ATLAS has become its flashpoint. For most of history, astronomy was the domain of professionals, people with access to telescopes, funding, training, and the institutional structures needed to publish research. Discoveries were made by observatories, announced through journals, and validated by peer review. The process was slow, careful, and gate-kept. If you wanted to contribute, you needed credentials, but technology has changed the game. Consumer cameras can now capture images rivaling research-grade instruments from decades ago. Software for stacking, calibration, and processing is free and powerful. Cloud computing makes heavy analysis accessible to anyone with a laptop, and social media provides instant distribution. An amateur observer in their backyard can process telescope data, spot an anomaly, and share it with thousands of people before a professional team even schedules a peer review meeting. This democratization has upsides. More eyes on the sky means more chance of catching rare transients, unusual events, subtle features that automated surveys might miss. Amateurs have discovered comets, asteroids, variable stars, and even exoplanet transits. They've contributed real science, published in journals, and earned respect from professionals. The barriers to entry are lower than ever, and the community is richer for it. But there are downsides too. Without standardized calibration, it's hard to trust the data. Without metadata, timestamps, instrument specifications, it's impossible to reproduce results. Without peer review, errors propagate unchecked, and without training in what artifacts look like, it's easy to mistake noise for signal, to see patterns that aren't really there. This is especially dangerous in low signal-to-noise environments like faint comets, where aggressive processing can turn random fluctuations into convincing-looking structures. The 3I-ATLAS controversy exemplifies this tension. Amateur astrophotographers claim they've uncovered anomalous structures through careful processing. They've shared their images online, and those images have gone viral, but professional astronomers using calibrated instruments and conservative processing don't see the same structures. They argue the amateurs have over-processed the data, introduced artifacts, and are misinterpreting the results. The amateurs counter that professionals are too cautious, too invested in standard models, and maybe even deliberately suppressing anomalies. Who's right? The honest answer is we don't know yet because the chain of custody is broken. The amateur images don't come with full provenance. We don't know exactly what raw frames they started with, what software they used, what parameters they chose. We can't reproduce their work, and without reproducibility, we can't validate their claims. This isn't a failure of honesty or effort, it's a failure of process. Contrast this with institutional science. When a professional team observes an object, they archive everything. Raw frames, calibration data, reduction scripts, final products. Other teams can access that archive, reprocess the data independently, and check the results. If a feature appears in multiple independent analyses using different pipelines, confidence grows. If it only appears in one pipeline, suspicion grows. This is how artifacts get identified and eliminated. But it requires infrastructure, standards, and time. The incentives are mismatched. For an amateur, the reward is discovery, recognition, maybe a bit of internet fame. Sharing a dramatic processed image that shows something unexpected brings attention. There's no penalty for being wrong, no peer review to fear, no reputation to lose. For a professional, the incentives are reversed. Caution is rewarded. Bold claims that turn out to be artifacts can damage careers. Publication takes months or years. The system favours conservative interpretations and discourages speculation. Neither incentive structure is ideal. Amateurs move fast but risk false positives. Professionals move slow but risk missing real anomalies. The ideal would be collaboration. Amateurs flag interesting features. Professionals validate or debunk them. Everyone shares data and methods openly. But we're not there yet. Instead, we have parallel conversations that barely intersect. Amateurs post on social media. Professionals publish in journals. The two communities speak different languages and operate under different norms. 3I-ATLAS could be a turning point. If the anomalous structures turn out to be real and were genuinely missed by professionals, that's a wake-up call. Institutions need to be more open to crowdsourced observations, more responsive to claims from outside, more willing to test unconventional ideas. But if the structures turn out to be artifacts, that's also a lesson. The crowd needs better standards, better training, better awareness of what can go wrong in image processing. Viral doesn't mean verified. What would best practice look like? Start with data sharing. Raw frames should be archived publicly with full metadata. Amateurs and professionals should have access to the same datasets. Next, open source processing. Pipelines should be documented, scripted, reproducible. If someone claims to see a feature, they should share not just the final image, but the entire workflow that produced it. Then, cross-validation. Multiple independent teams should reprocess the same data using different methods. If they all see the same structure, it's probably real. If only one team sees it, it's probably an artifact. We also need a cultural shift. Professionals need to take amateur observations seriously without dismissing them as noise. Amateurs need to accept that skepticism is part of the process, not an attack. And both need to recognise that the goal is truth, not winning an argument. That sounds idealistic, maybe naive, but it's the only way forward. The volume of astronomical data is exploding. Automated surveys are finding thousands of objects every night. No professional team can follow up on all of them. Crowdsourcing is inevitable. We might as well do it right. 3I-ATLAS is a test case. How we handle it will set precedents for future anomalies. If we get it right, we build trust, improve methods, and maybe even make genuine discoveries. If we get it wrong, we entrench divisions, spread misinformation, and waste the opportunity. In the next section, we're going to look at the social dynamics behind the controversy, the conspiracy theories, the information asymmetry, and what happens when trust breaks down between the public and scientific institutions. Part 9. Conspiracies, Information Asymmetry, and the Sociology of Uncensored Frames. Whenever official narratives and public perception diverge, conspiracy theories fill the gap. It's a pattern as old as human society. People see something strange, institutions downplay it, and the dissonance creates suspicion. Maybe the authorities are hiding the truth. Maybe they don't want us to know. Maybe there's a cover-up. The specifics vary, but the structure is always the same. We see more than they admit. Therefore, they're lying. 3I-ATLAS has triggered this pattern in full force. Online communities believe they've seen evidence of anomalous structures that official sources refuse to acknowledge. The processed images showing a rigid core and spiraling plasma are treated as forbidden knowledge, smuggled out by brave amateurs before the censors could suppress them. The professional denials are interpreted not as scientific judgment, but as institutional gatekeeping, maybe even deliberate deception. The narrative writes itself. They don't want you to know what's really out there. Let's map the actors. On one side, amateur astrophotographers and independent analysts, mostly operating through forums, social media, and video platforms. They have access to consumer-grade equipment, public telescope archives, and processing software. They're motivated by curiosity, sometimes by a desire for recognition, sometimes by genuine belief that they've found something important. They see themselves as outsiders challenging an entrenched establishment. On the other side, institutional scientists, NASA, ESA, professional observatories, university researchers. They have access to spacecraft data, large telescopes, advanced instruments, and peer-reviewed publication channels. They're motivated by scientific rigor, career advancement, and the reputation of their institutions. They see themselves as gatekeepers of quality, filtering signal from noise, protecting the public from misinformation. In the middle, the media and the public. Media outlets want stories that generate clicks, so they amplify the most dramatic claims without always having the expertise to evaluate them. The public wants answers, wants to know if something extraordinary is happening, and gets frustrated when experts hedge and equivocate. Trust in institutions is already fragile. When agencies say there's nothing to see here and amateurs insist there is, people don't know who to believe. The conspiracy claims centre on data manipulation. The argument is that official releases have been scrubbed or processed to remove anomalous features before being made public. Only raw frames, captured by independent observers or leaked by insiders, show the truth. The question is whether this is plausible. Technically, yes. Image processing is subjective. Choices about contrast, noise filtering, compression, even colour balance can emphasise or suppress different features. A sufficiently motivated actor could, in theory, use these tools to obscure something they didn't want seen. But practically, the logistics are prohibitive. 3I-ATLAS has been observed by dozens of telescopes in multiple countries. Hubble, JWST, Lucy, ground-based surveys, amateur networks. Each has independent data pipelines, different teams, different institutional cultures. Coordinating a cover-up across all of them would require conspiracy on a scale that's hard to imagine. Scientists are competitive, institutions are siloed, and leaks are common. Someone would talk. Someone always talks. There are simpler explanations. Professional data releases prioritize calibration and scientific fidelity over visual impact. Features that look dramatic in heavily processed amateur images might be below the noise threshold in conservatively processed professional images. That doesn't mean they were removed. It means they weren't reliably detectable. Timing and geometry matter too. Spacecraft might observe when the object is in a different orientation or activity state than when amateurs observed. Different instruments have different sensitivities. What one detector sees, another might miss. There's also institutional inertia. Space agencies are risk-averse. They don't want to make bold claims that turn out to be wrong, so they wait for peer review, for multiple confirmations, for consensus. That takes time. By the time they're ready to make a statement, the internet has moved on, and the narrative has solidified. Their denials come across as defensive or dismissive, even if they're just being careful. But let's acknowledge the legitimate grievance. There is information asymmetry. Agencies have access to data that the public doesn't. Raw spacecraft frames, high-resolution spectra, proprietary calibrations. When they release only processed images and summary statements, it creates a gap. People want to see the original data, want to process it themselves, want to verify the official conclusions. Withholding that data, even for good reasons like publication embargoes or proprietary rights, breeds suspicion. This has happened before in astronomy. Controversies over exoplanet detection, near-Earth asteroids, even the famous face on Mars. In each case, initial claims sparked excitement, official denials sparked suspicion, and eventually more data resolved the ambiguity. Sometimes the anomaly was real, sometimes it was an artifact. But resolution required transparency, independent verification, and time. The same is needed here. What would ideal transparency look like? Full public release of all raw spacecraft and professional telescope data on 3I-ATLAS, with metadata, calibration frames, and processing scripts. Open forums where amateurs and professionals can discuss their analyses. Collaborative reprocessing efforts, with multiple independent teams comparing results. New targeted observations designed to test specific claims, with results shared in real time. This is technically feasible. It just requires institutions to prioritize openness over caution. Will it happen? Maybe. Public pressure can move bureaucracies, especially when the stakes are high and the interest is sustained. But it requires the crowd to ask for the right things. not just demanding that agencies admit the comet is an alien probe, not just amplifying the most sensational claims, but asking for data, for reproducibility, for transparent methods, making it about science, not spectacle. The sociology here is fascinating and frustrating. We're watching two epistemologies collide. One says truth comes from consensus, peer review, institutional validation. The other says truth comes from direct observation, independent analysis, skepticism of authority. Both have value. Both have failure modes. The challenge is finding a synthesis, a way to combine the strengths of each while mitigating their weaknesses. 3I-ATLAS might be the catalyst for that synthesis, or it might be another chapter in a long history of distrust and talking past each other. Time will tell. In the next section, we're going to explore some of the more speculative physics ideas that have been floated to explain the anomalous observations. These are fringe theories, not mainstream science, but they're worth examining because they illustrate the limits of our current models and the kinds of phenomena we might encounter as we study more interstellar objects. Part 10: Alternative Physics and Fringe-Compatible Models. Science advances at the edges. The mainstream is where we have consensus, where theories are well tested and models are reliable, but the edges are where the action is, where anomalies lurk, where new ideas germinate. Most fringe theories turn out to be wrong. They fail to match observations, they violate established principles, or they're just too complicated to be plausible. But occasionally, something at the fringe turns out to be right, and the mainstream shifts. It's worth exploring these ideas, not because they're likely true, but because they stretch our thinking and prepare us for the unexpected. 3I-ATLAS, if it's genuinely anomalous, might require physics beyond standard comet models. Let's consider some possibilities. First, strong field plasma instabilities. Under certain conditions, ionized gas doesn't behave like a simple fluid. It can develop organized structures spontaneously. Filaments, vortices, rotating patterns. This happens in Earth's magnetosphere, in solar flares, in fusion reactors. The instabilities are driven by electromagnetic forces and can create coherent features that persist far longer than you'd expect from random turbulence. Could something similar be happening around 3I-ATLAS? If the comet is partially ionized and interacting with the interplanetary magnetic field, plasma instabilities might organize the gas into spiral or filamentary patterns. This doesn't require a magnetic core on the object itself, just the right conditions in the surrounding plasma. The problem is timescale. Plasma instabilities usually develop and dissipate quickly. Maintaining a coherent spiral over days or weeks would require sustained driving forces and very specific conditions. It's possible in theory, but requires fine-tuning that seems unlikely unless the object is doing something actively to sustain it. Second, magnetized dust aggregation. Dust grains in space can carry electric charge and respond to magnetic fields. If the dust is metallic or contains magnetic minerals, it could clump together under electromagnetic forces rather than just dispersing. This could create apparently solid structures that are actually loose aggregates, held together by fields rather than gravity. Think of iron filings around a magnet, but on a cosmic scale. Such structures could look rigid in images, but would be tenuous, fragile, easily disrupted. This is speculative, but not impossible. We know that dust plays a complex role in cometary comae, scattering light and interacting with solar radiation. Adding electromagnetic effects makes the behavior richer and harder to predict. But again, you'd need strong fields and conductive dust, neither of which are confirmed for 3I-ATLAS. Third, electrostatic cohesion models, sometimes called the electric comet or electric universe hypothesis. This idea proposes that comets are held together not by gravity or ice, but by electrostatic attraction between charged dust and rock grains. As the comet approaches the Sun, differences in charging create electric fields that can organize material into jets, tendrils, or other features. In extreme versions, the comet nucleus itself is an electrical discharge phenomenon, not a physical object at all. This is a fringe idea, rejected by mainstream planetary science because it conflicts with decades of observations and lab experiments. Comets have been visited by spacecraft. We've seen their nuclei up close. They're solid bodies, not plasma structures, but proponents argue that only electric models can explain certain features like the rapid brightening of distant comets or the appearance of jets before significant heating. For 3I-ATLAS, an electric model might predict that the core isn't metal, but a region of concentrated charge, and the Spiral is a discharge pattern. The challenge is making testable predictions. If the nucleus is electrically active, we should see signatures, radio emissions, X-rays, unusual spectral lines from high-energy excitation. So far, none of these have been reported. That doesn't disprove the hypothesis, but it weakens it. Fourth, and this is where things get really speculative, exotic matter or physics. What if 3I-ATLAS is made of something we don't have a name for? A relic from the early universe, a fragment of strange matter, a dark matter condensate that happens to interact with normal matter under certain conditions. These ideas are the domain of theoretical physics, not observational astronomy. They're fun to think about, they make for great science fiction, but they're not useful scientifically unless they make predictions we can test. For instance, if 3I-ATLAS were a dark matter clump, it should interact gravitationally but not electromagnetically. It wouldn't emit light, wouldn't have a coma, wouldn't be visible at all. The fact that we see it, that it has a coma and a tail, rules out pure dark matter. You could propose hybrid models, dark matter core with normal matter veneer, but now you're adding complexity to save a hypothesis that wasn't necessary in the first place. Occam's razor cuts these ideas down quickly. What all of these fringe models have in common is that they're trying to explain observations that may not be real. If the anomalous structures in the processed images are artifacts, then none of these models are needed. The object is just a comet, and we're wasting time on unnecessary speculation. But if the structures are real, then we need new physics, or at least new applications of known physics to explain them. That's the dilemma. Here's what would settle it. High-resolution spectroscopy looking for emission lines from ionized metals, which would support the magnetic core hypothesis. Polarimetry to probe dust and plasma properties, which could reveal electromagnetic organization. Long-term monitoring to see if the spiral structure persists or evolves, which would test whether it's a transient instability or a stable feature. In situ measurements, if a probe could be sent, to directly sample the coma and measure fields and particles. These observations are technically feasible. They just need funding, telescope time, and institutional will. Until then, the fringe models remain speculative. They're intellectually interesting, they push boundaries, but they're not science in the full sense until they're tested. The danger is that they become attractive precisely because they're unverified, because they offer an exciting alternative to the mundane truth. We need to resist that temptation. Excitement is good, but evidence is better. In the next section, we're going to zoom out from 3I-ATLAS itself and look at the broader context of discovery and technology in 2025. How are advances in AI, machine, learning, and image analysis changing the way we handle anomalies? What can other recent breakthroughs in fields like fusion and gravitational wave astronomy teach us about how to approach ambiguous data? And what does this moment say about where astronomy is headed in the next decade? Part 11, AI and the Model Race. How next-generation tools change the verification game. 2025 is a year of acceleration, not just in space exploration or astronomical discovery, but in the tools we use to make sense of what we're seeing. Artificial intelligence has crossed thresholds that were speculative just a few years ago. Models can now analyze images, detect anomalies, cross-reference databases, and even suggest physical interpretations all in seconds. This isn't science fiction. It's happening now, and it's about to change how we handle controversies like 3I-ATLAS. Imagine feeding the contested processed images of 3I-ATLAS into a next-generation AI trained on millions of astronomical images. The system has learned what artifacts look like, halos from overprocessing, edge enhancement residuals, noise patterns, diffraction spikes. It has also learned what real structures look like: jets, spirals, fragmentation events, morphological features seen in other comets and asteroids. The AI compares the 3I-ATLAS images to both categories and flags regions of concern. Is the core real or an artifact? Is the spiral consistent with known plasma dynamics or just amplified noise? This capability is coming online right now. Models like hypothetical successors to current multimodal systems can ingest not just the images themselves, but the metadata, the processing history, even the telescope specifications. They can run simulations, compare against databases, and produce probabilistic assessments. This is more than pattern recognition. It's automated scientific reasoning, and it has profound implications. For the 3I-ATLAS controversy, An AI-based audit could cut through the ambiguity. If the system flags the processed images as unstable, likely to contain artifacts, that's evidence against the anomaly. If it confirms persistent structure across independent observations and processing pipelines, that's evidence in favour. Either way, it moves the conversation forward, and because the AI's reasoning can be inspected, its judgment can be validated or challenged by humans. It's not a black box replacing scientists, it's a tool augmenting them. But there are risks. Over-reliance on AI can create new failure modes. If everyone trusts the algorithm's verdict without checking the logic, mistakes propagate. If the training data is biased, the AI will inherit those biases. If the model is tuned for speed over accuracy, false positives and false negatives creep in. We're replacing one set of problems with another. The key is keeping humans in the loop, using AI to flag issues and propose explanations, but leaving the final judgment to people who understand the physics and the context. This technology also democratizes verification. Right now, only professionals with access to expensive software and computing clusters can do rigorous artifact analysis. But if AI tools become widely available, amateurs can use them too. That levels the playing field. An independent observer can process raw frames, run an AI audit, and produce results that are taken seriously by the community. Or they can have their claims debunked quickly and definitively if the AI shows they've introduced artifacts. Either way, transparency improves. As 3I-ATLAS fades from view and future interstellar visitors are discovered, this capability will be crucial. Surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time will generate terabytes of data every night. Humans can't review it all. AI will have to do the first pass, flagging anomalies, identifying candidates for follow-up. If we get the tools right, we'll catch things we'd otherwise miss. If we get them wrong, we'll drown in false alarms. The other lesson from AI development in 2025 is the importance of open source and collaboration. The best models are being built by teams that share code, publish methods, and invite scrutiny. That's the culture we need in astronomy too. If an AI system is used to make a scientific claim, the model's weights, training data, and decision logic should be available for inspection. That's how trust is built. That's how errors are caught. That's how science advances. 3I-ATLAS might be remembered not for what it is, but for what it taught us about how to investigate. The images, the claims, the controversy, they're all data points in a larger process of figuring out how to do astronomy in an era of big data and viral media. AI is part of the solution, but only if we use it wisely. In the next section, we're going to look at another technological frontier, advances in magnetic field generation and plasma control here on Earth, and what they might tell us about the plausibility of a magnetized object like 3I-ATLAS, existing naturally or otherwise. Part 12, Fusion Magnet Breakthroughs on Earth. Earth Labs meet cosmic speculation. While astronomers debate what 3I-ATLAS might be, engineers on Earth are building devices that look a lot like what some people imagine it to be. Magnetic confinement fusion reactors, devices designed to hold superheated plasma in place using powerful magnetic fields, have achieved remarkable milestones in 2025. Tokamak Energy, among others, announced sustained operation of ultra-strong magnets generating fields exceeding 10 Tesla, holding plasma at temperatures hotter than the core of the Sun. This is engineering, not speculation. We're building machines that do what the dynamo hypothesis says 3I-ATLAS might be doing, generating strong magnetic fields and controlling the flow of ionized gas. The analogy is seductive. If we can build a magnetic bottle for fusion plasma here on Earth, why couldn't nature or another intelligence build something similar on a larger scale? A comet-sized magnetized core with plasma spiraling around it isn't fundamentally different from a fusion reactor, just scaled up and operating in a different environment. The physics is the same. Charged particles moving in magnetic fields, Lorentz forces, magneto-hydrodynamic instabilities, all the phenomena we see in terrestrial experiments, but scale matters. A fusion reactor is a few meters across, encased in tons of superconducting magnets, cooled with liquid helium, powered by megawatts of electricity, and monitored by thousands of sensors. It's one of the most complex machines humans have ever built. Scaling that up to a kilometer-sized object operating autonomously in interstellar space for millions of years is a leap of many orders of magnitude. The The engineering challenges aren't just difficult, they're existential. Where's the power source? How do you maintain superconductivity without active cooling? How does the structure survive micrometeorite impacts, cosmic rays, thermal cycling, and gravitational stresses? For a natural object, the problems multiply. Planetary cores can be magnetized, yes. Earth's core generates a dynamo through convective motion of molten iron. But Earth is massive, geologically active, and has an internal heat source from radioactive decay. A small metallic fragment wandering through interstellar space would cool quickly, solidify, and lose any dynamo activity. The only way to sustain a magnetic field is if the object is still warm inside, still convecting, or if it has some other energy source we don't understand. This is where the artificial hypothesis starts to look less crazy. If 3I-ATLAS really is a dynamo, the engineering explanation might be simpler than the natural one. A machine designed to sustain its magnetic field could use energy from cosmic rays, from motion through the interstellar medium, or from stored power sources like radioisotope generators or even fusion. It could be built with materials and technologies that we don't have yet but that a more advanced civilization might. It could be designed to last millions of years, hibernating during the long interstellar journey and activating when it enters a stellar system. But this is speculation built on speculation. We don't have evidence of artificiality. We don't even have confirmed evidence of magnetic activity. What we have are ambiguous processed images and a lot of questions. Using terrestrial fusion breakthroughs as evidence for 3I-ATLAS being a dynamo is a reverse inference fallacy. Just because we can build something doesn't mean it exists in space. Most things that are possible don't actually happen. Still, the thought experiment is valuable. It clarifies what we should look for. If 3I-ATLAS really is generating magnetic fields, we should detect them. Spacecraft with magnetometers flying nearby could measure field strength and geometry. Observations of how the plasma tail responds to changes in the solar wind could reveal magnetic coupling. Radio emissions from charged particles spiraling in magnetic fields could be detected from Earth. These are specific testable predictions. If the dynamo hypothesis is correct, at least some of these signatures should exist. If they don't, the hypothesis is wrong. So far, no magnetic field has been detected, no radio emissions reported. The plasma tail in professional images looks like a normal comet tail. This doesn't prove the hypothesis wrong, but it doesn't support it either. The burden of proof remains high. Extraordinary claims need extraordinary evidence, and right now the evidence is marginal at best. The lesson from fusion research is that building and sustaining magnetic confinement is hard, even with human ingenuity and massive resources. Expecting nature to do it casually, or expecting an alien civilization to have done it and sent the result wandering through our solar system, requires strong justification. It's possible, yes, but plausible, that's where the argument gets shaky. In the next section, we're going to draw a parallel with another field, gravitational wave astronomy, where the community has developed rigorous methods for handling marginal signals and ambiguous data. What can we learn from their approach? Part 13. Methodological Parallels. Lessons from Gravitational Wave Anomaly Hunts. Gravitational wave astronomy is in many ways the perfect model for how to handle anomalies in noisy data. When LIGO and Virgo detect a signal, it's buried in noise. The detectors are so sensitive they pick up everything: seismic vibrations, thermal fluctuations, quantum shot noise, even the sound of waves hitting distant coastlines. The challenge is to extract real astrophysical events from this chaos without getting fooled by glitches, instrumental artifacts, or statistical fluctuations. The community has developed sophisticated methods. Multiple detectors observing simultaneously reduce false positives. Statistical thresholds are set conservatively to keep the false alarm rate low. Every candidate event is checked against glitch catalogues, environmental monitors, and auxiliary sensors. Pipelines are cross-validated. Independent teams analyze the same data using different algorithms. Only when multiple lines of evidence converge do they claim a detection, and even then, the result is reported with statistical significance, not certainty. This is the gold standard for handling ambiguous data. It's slow, it's conservative, but it works. Over the past decade, LIGO and Virgo have detected dozens of black hole and neutron star mergers. Initially, some signals were disputed, suspected of being glitches or artifacts, but the rigorous methodology resolved the ambiguities. Some candidates were confirmed, others were rejected, and the field moved forward with confidence. 3I-ATLAS could benefit from the same approach. Treat the processed images as candidate detections, flag them for follow-up, apply multiple independent processing pipelines, check for artifacts systematically, look for cross-confirmation from different instruments and different dates, set statistical thresholds. How confident do we need to be before claiming the structure is real? Use simulations to understand what artifacts might look like and how to distinguish them from genuine features. This hasn't happened yet, at least not publicly. The processed images appeared online, sparked excitement and debate, but there's been no coordinated, systematic verification effort, no consortium of teams reprocessing the data, no published papers comparing pipelines, no statistical framework for evaluating confidence. The conversation has been driven by social media virality, not scientific process. The gravitational wave community also teaches another lesson: the importance of patience. When a marginal signal appears, the first response isn't to hold a press conference. It's to dig deeper, collect more data, run more tests. Sometimes this takes months or years. The public might get impatient, but the science benefits from the delay. False alarms are avoided, and when a real detection is announced, it's solid. Applying this to 3I-ATLAS means accepting that we might not know the answer for a long time. More observations are needed, more processing attempts, more cross-validation. Maybe years from now a consensus will emerge, or maybe the object will fade from view before we resolve the controversy, leaving it as an enduring mystery. That's frustrating, but it's honest. There's also a cautionary tale from gravitational waves. In the early days, the field was plagued by claims and counterclaims, with some researchers seeing signals that others couldn't reproduce. This led to skepticism and damaged the field's reputation. It took years of rigorous methodology and transparent collaboration to rebuild trust. The lesson: premature claims hurt everyone. Better to be slow and right than fast and wrong. 3I-ATLAS is at risk of following that path. If the anomalous structures turn out to be artifacts, and the claims are eventually debunked, the credibility of amateur processing will suffer. Future genuine discoveries might be dismissed as noise. Conversely, if the structures are real and professionals ignored them, the credibility of institutional science suffers. Either way, the stakes are high. The only way to navigate this is with rigor, transparency, and humility. In the next section, we're going to look at what other recent discoveries, particularly from JWST, tell us about the diversity of cosmic materials and how 3I-ATLAS fits into that broader context. Because even if it's not a magnetic dynamo or an alien probe, it's still teaching us something important about the variety of objects out there. Part 14, Cosmic Materials Context. What other discoveries tell us about interstellar diversity? 2025 has been a banner year for cosmic chemistry. The James Webb Space Telescope has been returning data that's rewriting our understanding of what materials exist in the universe and how they're distributed. Observations of exoplanet atmospheres have revealed exotic chemistries: silicate clouds raining molten glass, atmospheres rich in carbon monoxide and methane, temperature gradients that challenge atmospheric models. Observations of star-forming regions have shown complex ices coating dust grains, water, methanol, ammonia, carbon dioxide, but also more surprising molecules like formaldehyde and acetylene in unexpected ratios. This diversity matters for 3I-ATLAS. We're learning that our solar system's inventory of materials might not be representative of the galaxy as a whole. Different protoplanetary disks form under different conditions, different temperatures, pressures, radiation environments, chemical abundances. The objects that form in those disks will reflect those conditions. An interstellar visitor might bring materials or compositions we've never seen before, not because they're artificial or exotic, but because they formed somewhere else under different rules. The JWST observations of 3I-ATLAS fit into this picture. The near-infrared spectrum shows a CO2-dominated coma, which is unusual but not unprecedented. CO2 is more volatile than water, sublimating at lower temperatures. Finding it as the dominant component suggests that 3I-ATLAS formed in a region of its original protoplanetary disk, where CO2 ice was abundant, likely near the CO2 ice line farther from its parent star than the water ice line. This implies a cold formation environment, consistent with the object being a comet from the outer regions of another stellar system. But there are also puzzles. The dust in the coma has unusual properties. Polarimetric observations show a deep negative polarization branch, meaning the dust grains scatter light in a way that's different from typical solar system comets or asteroids. This could indicate different grain sizes, different compositions, maybe more porous or more compact structures. The exact interpretation is still debated, but the point is clear. 3I-ATLAS is compositionally distinct. It's not just another Oort cloud comet that wandered in from our own system. It's genuinely foreign. This is exciting even without invoking dynamos or aliens. Every interstellar object we study expands our understanding of planet formation and system evolution. We've only confirmed 3 so far: 1I/Oumuamua, 2I/Borisov, and now 3I-ATLAS. That's a tiny sample. Each one shows different properties. Oumuamua was elongated, tumbling, with an unexplained non-gravitational acceleration. Borisov looked like a normal comet, with water and carbon monoxide outgassing. Atlas is CO2-rich, with unusual polarization. If we extrapolate from 3 objects to the billions that must exist, the diversity is staggering. Every possible combination of ices, rocks, metals, organics probably exists somewhere. Some might look familiar, others might be completely alien. But here's the key insight. Alien doesn't mean artificial, it just means different. 3I-ATLAS challenges our assumptions, yes. It doesn't fit neatly into the categories we've built from studying solar system objects. But the universe is under no obligation to conform to our categories. It's richer, weirder, more varied than any taxonomy can capture. That's humbling, but it's also inspiring. We're at the very beginning of understanding the cosmic inventory. Every new object is a gift, a chance to learn. So even if the processed images turn out to be artifacts, even if the magnetic dynamo hypothesis collapses, 3I-ATLAS still matters. Its unusual composition, its CO2 dominance, its polarization signature, all of these are real and worth studying. They tell us about conditions in other stellar systems, about the diversity of planetary building blocks, about the processes that shape objects over billions of years. That's the baseline science, the solid ground beneath the speculation. And if, against the odds, the anomalous structures turn out to be real, if there really is something happening with 3I-ATLAS that we don't understand, then the payoff is even greater. We'd be forced to expand not just our taxonomy of objects, but our understanding of physics. New mechanisms, new phenomena, new possibilities. That's how science grows. Not by confirming what we already know, but by confronting what we don't. In the final section, we're going to tie all of this together. What does 3I-ATLAS teach us about the state of astronomy in 2025? What should we watch for in the coming months? And how should we, as curious humans trying to make sense of the cosmos, approach anomalies like this? Part 15. Why Anomalies Matter. The 2025 Astronomy Paradox and a Watch List. Let's step back and look at the bigger picture. 2025 is a paradox. We're living through an era of unprecedented discovery. Telescopes more powerful than ever before. Data pouring in faster than we can analyze it. AI tools that can spot patterns humans would miss. The universe is opening up in ways that would have been unimaginable a generation ago. And yet, we're also more uncertain, more divided, more prone to confusion than ever. The tools that enable discovery also enable misinformation. The openness that democratizes science also fragments consensus. We see more, but we understand less. 3I-ATLAS embodies this paradox. We have images from spacecraft and ground observatories, spectra from the most advanced telescope ever built, observations spanning months and multiple wavelengths. But we still can't agree on what we're looking at. Is it a comet or something else? Are the processed images showing real structures or artifacts? Should we trust the professionals or the amateurs? The data is abundant, but clarity is elusive. This is the new normal. As surveys like the Vera Rubin Observatory come online, as more interstellar visitors are discovered, as citizen science grows and AI tools proliferate, we're going to encounter more anomalies. Some will be genuine discoveries, some will be artifacts, many will be ambiguous, suspended between confirmation and debunking for months or years. We need to get better at handling this ambiguity. We need patience, rigor, and intellectual humility. We need to resist the urge to jump to conclusions, either dismissive or sensational. The challenge isn't just technical, it's psychological. Human beings are pattern-seeking creatures. We evolved to see faces in clouds, to find meaning in randomness, to connect dots even when no connection exists. This served us well on the African savannah, where mistaking a shadow for a predator was safer than the alternative. But in astronomy, where we're dealing with noise, artifacts and data at the limits of detection, this tendency becomes a liability. We see what we want to see. We interpret ambiguity in ways that confirm our existing beliefs. Professional scientists are trained to resist these biases, but they're not immune, and amateurs, operating without that training, are even more vulnerable. At the same time, dismissing every anomaly as artifact or bias is equally dangerous. Real discoveries often start as anomalies that don't fit existing models. Pulsars were initially called little green men because their regular signals seemed too organised to be natural. Quasars were thought to be stars until we realised they were galaxies billions of light-years away. The cosmic microwave background was initially attributed to pigeon droppings on the antenna. Science advances by taking anomalies seriously, investigating them rigorously, and being willing to revise models when the evidence demands it. The trick is knowing which anomalies deserve serious investigation and which are noise. 3I-ATLAS sits in that uncomfortable middle ground. There's enough there to warrant attention. The processed images are striking. The claims are specific. The potential implications are enormous. But there's also enough uncertainty to justify skepticism. The structures haven't been independently confirmed. The spectroscopy doesn't support exotic composition. The trajectory shows no anomalies. Professional teams with better instruments and rigorous methods see a comet. So which interpretation do we trust? Here's what to watch in the months ahead. First, raw data releases. If NASA, ESA or other agencies make unprocessed spacecraft frames available with full metadata, that's a game changer. Independent teams can reprocess, compare and settle the artifact question definitively. Demand this, not with conspiracy theories but with reasoned arguments for transparency and reproducibility. Science is strongest when data is open, when methods are transparent, when anyone with the skills can verify or challenge the conclusions. If the agencies believe their interpretation is correct, they should welcome independent analysis. If they're confident the anomalies are artifacts, they should provide the data that proves it. Second, spectroscopic campaigns. If any team reports detection of nickel, iron or other heavy metal emission lines from 3I-ATLAS, that's major. It would support the metal core hypothesis and demand serious follow-up. Such a detection would need to be high signal to noise, calibrated, reproducible and published in peer-reviewed literature. Colour impressions and visual estimates don't count. We need actual spectral lines at the right wavelengths with the right profiles. Conversely, if high-resolution spectra continue to show only normal cometary volatiles, carbon dioxide, water, organics, dust, that weakens the exotic interpretations, it doesn't eliminate them entirely, but it makes them harder to justify. Third, polarimetry and multi-wavelength studies. How does the coma and tail evolve as the object recedes? Does the polarization behavior remain unusual? Are there wavelength-dependent features that reveal dust or plasma properties? These observations are less dramatic than spectral detections, but equally important for understanding composition and dynamics. Polarization tells us about grain size, shape, and composition. Multi-wavelength observations reveal temperature gradients, chemical distributions, and activity patterns. Together, they build a complete picture of what 3I-ATLAS really is. Fourth, AI-based reanalysis. As machine learning tools become more accessible, watch for teams applying them to 3I-ATLAS data. An AI audit that flags artifacts or confirms structures would move the debate significantly. Bonus points if the analysis is open source and reproducible. The advantage of AI is that it can process vast amounts of data, compare against thousands of reference images, and detect subtle patterns or artifacts that humans might miss. But the disadvantage is that AI can also inherit biases from its training data, or produce false positives if not carefully validated. Any AI-based claim needs to be backed up by human interpretation and cross-checked against independent methods. Fifth, trajectory monitoring. Keep tracking the object's path as it leaves the solar system. If non-gravitational accelerations deviate from expectations, if they show time variability or direction changes inconsistent with outgassing, that's a clue. Conversely, if the trajectory remains boringly predictable, that's evidence against electromagnetic activity. The beauty of astrometry is that it's hard to fake. Positions measured by multiple observatories, tracked over weeks and months, create a dataset that's robust and reproducible. If 3I-ATLAS were truly a magnetized object interacting with the solar wind, it should show trajectory perturbations that don't align with standard comet models. The absence of such perturbations doesn't prove the hypothesis wrong, but it weakens it considerably. Sixth, future interstellar visitors. We're entering an era where these objects might be detected regularly. Each one will test our models and expand the sample. If future visitors show similar anomalies, that's a pattern worth investigating. If 3I-ATLAS remains unique, that suggests its features are rare or artifact-driven. Sample size matters in science. 1 anomaly is interesting. 2 is a coincidence. 3 or more is a pattern demanding explanation. We need more data points, more interstellar objects observed with the same rigour, before we can draw firm conclusions about whether 3I-ATLAS is typical or exceptional. What should you, as someone curious about all this, actually do? Stay sceptical but open-minded. Don't jump to conclusions based on a single dramatic image or claim. Wait for multiple lines of evidence. When experts disagree, try to understand why. What data are they looking at? What assumptions are they making? Who has the stronger argument, not the louder voice? Science isn't about authority or credentials, it's about evidence and logic. A well-reasoned amateur analysis can be more valuable than a poorly argued professional opinion. But claims need to be backed by data, methods need to be transparent, and conclusions need to be proportionate to the evidence. Support transparency. If you encounter claims that agencies are hiding data, ask for specifics. What data, from which instrument, observed when? If there's a legitimate gap, advocate for filling it. But don't assume malice where incompetence or institutional inertia might suffice. Bureaucracies move slowly. Data release takes time. Publication schedules lag behind discovery. These are frustrating realities, but they're not evidence of conspiracy. Push for openness, yes, but do it with specific requests and reasonable expectations, not vague accusations. Recognize that anomalies have value even when they turn out to be wrong. 3I-ATLAS, whether it's a comet or something stranger, has sparked conversations, inspired people to learn about comets and spectroscopy and orbital mechanics. It's pushed amateur astronomers to refine their methods and pushed professionals to communicate better. That's progress, even if the specific claims don't pan out. Every controversy is a teaching moment, an opportunity to explain how science works, how data is processed, how conclusions are drawn. The public engagement around 3I-ATLAS has been extraordinary. People who never thought about comets before are suddenly curious about spectroscopy, magnetic fields, image processing. That curiosity is valuable regardless of what 3I-ATLAS turns out to be. And finally, remember why this matters. Not because 3I-ATLAS might be an alien probe, though that would certainly be exciting, but because every interstellar visitor is a messenger from another world, a sample of cosmic diversity, a reminder that the universe is larger and stranger than our imaginations. We're at the very beginning of studying these objects. 3I-ATLAS is just the third confirmed. There will be more. Each one will surprise us. Each one will challenge our models. Each one will teach us something. The universe doesn't owe us easy answers. It doesn't package discoveries in neat, unambiguous forms. Nature is messy, data is noisy, and truth emerges slowly through the accumulation of evidence and the refinement of understanding. 3I-ATLAS is teaching us to be comfortable with uncertainty, to live in the questions rather than rushing to answers, to balance excitement with skepticism. So as 3I-ATLAS recedes into the darkness, fading below detection thresholds and becoming just another entry in astronomical catalogues, the questions it raised remain, not just about this one object, but about how we do science, how we handle uncertainty, how we collaborate across the professional-amateur divide, how we use AI and open data, how we communicate with the public. These are the meta-questions, the ones that matter beyond any single discovery. We're learning, slowly and messily, how to be a species that studies the cosmos, not just from a few elite observatories, but from thousands of locations with millions of curious minds. That's the real revolution. 3I-ATLAS might or might not be a magnetic dynamo, but it's definitely a catalyst, and that, in the end, might be its greatest contribution. It's showing us what astronomy looks like when barriers fall, when data becomes accessible, when curiosity drives investigation rather than credentials. It's messy, it's contentious, it's exciting, it's the future. Welcome to the new age of astronomy, a time when discoveries can come from anywhere, when anomalies spark global conversations within hours, when the line between professional and amateur blurs into irrelevance. A time when we're challenged not just to observe the universe, but to think carefully about how we observe, how we interpret, how we communicate what we find. 3I-ATLAS is our training ground. The lessons we learn here will shape how we handle the next interstellar visitor, and the one after that, and all the strange objects yet to be discovered. Stay curious, stay skeptical, keep asking questions, demand evidence, but remain open to surprise. And above all, keep watching the skies, because out there in the darkness between stars, more visitors are coming, each one carrying secrets from distant worlds, each one challenging us to understand, each one reminding us that we've barely begun to comprehend the cosmic neighborhood we inhabit. The adventure is just beginning.